would be continuing with some high-end designs. So just to give a brief overview, I would like to cover on a few two basic example codes by keeping in view of third year and fourth year BTech students. Yeah, next I would like to highlight the job opportunities in the industrial aspects with respect to this course. So this course is mainly focused on FPGA based digital VLSS system design, and when if you are taking into consideration the current market scenario, there are quite a very good job opportunities available in this field. And as per industry standards, what they will do is uh, in order to fill this position they have various designations. So once you get familiarized with the FPGA based design flow, and at the same time you are very good at RTL coding, that is by any of the HDL language, either VHDL or Verilog, then you'll be having very good opportunities. You can go into the industry as a RTL design engineer or an FPGA design engineer. Just a minute. Yeah, FPGA design engineer, so on and so forth. The designations will vary from company to company, but the main job role will be taking the specifications, then describing the circuit in HDL language, and then synthesizing the RTL to gate level netlist and mapping this gate level netlist either into uh, circuit or layout level if you take into consideration of ASIC design flow, or else if you are only sticking with FPGA design flow, then mapping the gate level netlist into uh, FPGA based implementation. So, as a beginner, you may expect around 12 LPA to 16 LPA if you have a very good hands-on experience on these courses. If you have some around 5 to in between 5 to 10 years of experience, you can expect a salary of around 24 to 30 LPA, and the pay scale will increase further with respect to the experience that you gain in this EDA environment. So basically, you can choose either any one field. Either if you want to move in the FPGA based field, you can move, or else if you want to move in the ASIC flow, that is also fine. Uh, Try to get specialized in any one of the field. Again, in ASIC we have covered so many things, right? So again, there is a front end and a back end. So front end mainly discusses on description to RTL HDL, and from there to gate level netlist, and from there some static timing analysis and all. At the back end mainly focuses on placement, floor planning, placement, routing, and then chip tape out. So again, at the front end, you also have a one area that I have not covered, that is called DFT. So DFT is called design for testability, for verifying the end chip functionality, and also for checking the process related defects, maybe stuck at 1 or stuck at 0. So there are some kind of defects which will come into a chip at the time of a process, while processing. So we call these as process variations. So there are so that these all things are handled by the DFT engineers. So similarly, again, if you take verification, that is a separate entity. So there are some methodologies like UVM, OVM methodologies, mainly purely based on verification. So if you want, if you are interested in verification field, you can also go there. So there are a lot of opportunities available because the demand is very high in the global market and the skilled manforce is very less. And due to the outbreak of COVID-19, we can also see like there is a outcome of a global chip shortage. I think you might be aware of. So This has given, fortunately or unfortunately, in the current trend, the industry is offering more number of job positions in the VLS. So you will be having a very good scope in the core field. So let's hope for the best. I expect like you'll be having a very good hands-on experience, and you'll also be enhancing your skills and capabilities to this activity. Okay, so without wasting further time, let's jump into this second session. I hope everyone have installed successfully the Xilinx Vivado software tool in your laptops. Even if it is still undergoing, there won't be any issue. As I discussed with Dr. M. Mahesh, he said that the sessions will be recorded. You can, I will be doing the coding from my end, and I will be demonstrating the flow. You can just note down the steps. Uh, if your installation has not yet completed, if your installation is done and if you're ready, then you parallelly do the steps, follow my instructions and do the steps, so that you'll be getting a real-time experience. So okay, so allow me to share my screen. Yeah, can anyone please confirm whether my screen is visible or not?
Yes, sir, visible, sir.
Okay, okay. Thank you very much for the feedback, sir. So, in my laptop, I think Vivado 2021.1 has been installed. So I can find an icon on my desktop. Similarly, you can also find a similar kind of a shortcut on the desktop. Even if it is not there, just go to programs and search for Vivado. I think you might have installed 2022.1. So just double click on it, and it will take at least some 30 seconds to boot it up. Actually, in the first session, I forgot to show this picture. Actually, I was discussing about the level of abstractions, right? So on top, we have a system. One level hierarchy, we have a module. From the module, we be having gate level netlist gates. From the gates, we have a circuit. From the circuit, we have a device. Device is nothing but a single transistor. So at various levels of hierarchy, design engineers will be working in each and every field at the device level, at the circuit level, gate level, module level, and system level. When coming to the digital VLSI system design using FPGAs, we will be working at the system level. So our specifications will be with respect to the system. So we take the specifications with respect to a system, and then we partition the system into a number of modules. For each module, we will develop an RTL HDL description code either by VHDL or Verilog. I am familiar with Verilog language, so throughout these sessions, I will discuss the descriptions of hardware in Verilog. You can, if even if you are a beginner in Verilog, not an issue. You can just follow me, and later I will give you few reference links where you can have a good expertise in Verilog by going through few reference materials. If you're comfortable with VHDL, you're not an issue. You can also do it in VHDL. So for each and every modules, we'll develop a Verilog codes, and then we will synthesize into the gate level netlist. And from the gates, we will directly implement it on the FPGA based netlist, and we will generate a bit stream, and we will program the FPGA, and we will realize the hardware. In the ASIC flow, from the gate level, we'll go to circuit level, circuit to device level. So this is the top-down approach in a typical VLSI design flow. So I hope a Vivado tool is opened in all the laptops. Individual users who are able to who are going to do the hands-on session along with me. So if I'm running fast, then you do please do acknowledge me. I will just slow down my explanation. So is it good to go?
Yes,
Shall I proceed?
yes, then you can proceed.
Yeah, someone please be give a feedback so that I can understand it.
Yes, sir, you can proceed, sir.
Okay, okay, okay. So once you invoke the tool, you'll be landing into the home page of Vivado, where you'll be having it is divided into two parts. So on the right hand side, you can see if you have opened any recent projects, it will list you out the recent projects that you have already worked on. On the left hand side, you will be having few guidelines with from where you can begin your work. So under the quick start, you click on create project. So we are going to create a new project by creating a new environment. So in that environment, we will be developing our first uh, hardware architecture. So once you click on the create project, you will get a new project window. So it is asking you to create a new Vivado project. So you can just read the three lines. So it is also saying the same. So you click on the next button. Now it is asking you to enter the project name and project location. So what I do is as per your desired location, you can browse it to any location of your choice. So what I am doing is in my PC on the desktop, I have an FDP folder. In that FTP folder, I have day one. So that directory I will set it as my project location, and the name of the project that I am going to give it as lab underscore one. So in day one, we are doing the first lab experiment. So that is the scenario. Here on the left, the bottom side, you can see create project subdirectory. It is by default, it is a check mark is available. If you remove that, what it will do is in the last directory itself it will dump all the files. So in my location I have a day one folder. In day one I will be doing two or three experiments, and all experiments I need it in a different folder. So if I don't select this checkbox, all the files it will dump in day one folder, whatever the experiments I'm doing. So all experiment files will be clubbed together, so it will create a mismatch. So even it will be difficult for you to track it. So that's why always check that the checkbox is enabled, so that for each and every project name a dedicated directory is selected in the destination path what you have selected, and then click on next. And here it is asking you what is the project type that you are going to do. So by default it is selected to RTL project. Don't bother about other type of projects, so that is of not our interest. So we are only basically interested in RTL project, so make sure that RTL project is enabled. Under the RTL project, two selection boxes. In the old version, I think it will show only one selection box. If anyone is using an older version, so for you, I'm telling. So it is asking, do not specify sources at this time. What does this means? Actually, we are creating our new project and we are going to design our new hardware architecture. Assume that you already have designed your architecture and that you are going to import. Then you can uncheck that box and you can provide the sources while creating the environment itself. Then environment along with the sources will be prepared. So we are doing it from scratch. So as of now we assume that we don't have any sources and we need to build the sources in the sense the hardware architecture in the form of a Verilog HDL description. So now we do not have any sources. That's why we have checkbox. In the checkbox we have selected like do not specify sources at this time. And don't select the second box, that is a whitish platform, that is mainly used for SOC design. So that we will check at the on, I think, on the fifth day. So after RTO project, click next. Now it is asking you to select the target device. So ultimately your goal is, after developing the hardware architecture, finally you have to implement the hardware architecture on any FPGA target. So it is mandatory for you to select the target at the initial stage of the development of the project. Later also, in the later stage, you are also free to change the target, but at the initial stage itself, you need to specify uh, any of the target. Maybe you may not use the target, and you in the later stage you can also have the flexibility to change the target. So what I have done is I have sent dedicated FPGA kits to your institution. So I think students might be having the access to that. In that there are two beginner kits, that is basis 3 FPGA. If you are able to see it, you can just have a look into it. So for today's experiment, we'll be using with a basic beginner level entry development board from Xilinx. Since we are using Xilinx Vivado, Vivado is a EDA tool for FPGA designs provided by Xilinx. So the FPGA target also must be a Xilinx family based FPGA. Otherwise, you won't be able to implement the design. Only you can just simulate the design. So since now you are having access to only one particular board, so what I have to do is I need to enter the details of that development board which you are having currently. So if you look onto the board, you can find the part number. It is written as XE7A35T CPG 236 minus 1. uh, Otherwise you can also fill all these fields if you are new. So under the first category you can select general purpose FPGA. So FPGAs also come with different classes. Automotive based FPGA category is there, we use it for automotive applications. General purpose, as the name suggests, generally is used. Some FPGAs are only specially used for military applications, so there are military and high reliability FPGAs. And some FPGAs maybe they will be used for aerospace applications. You know that in space we have a lot amount of radiation, so the hardware which you are designing should be radiation tolerant FPGAs. So there are specialized FPGAs where they are radiation hardened FPGAs are also available. So the category, those FPGAs fall under the category of radiation tolerant. So our FPGAs which now you are having in your lab fall under the category of general purpose. And family, as I mentioned, it is a development board having an Arctic 7 FPGA. The development board name is basis 3. It comes with a FPGA that belongs to a family of Arctic 7. So under the family you select Arctic 7, and that Arctic 7 has various types of packages. The package of the FPGA that is sitting on the basis tree development board is CPG 236, and the speed grade of that FPGA is -1. So after giving all these things, then the FPGAs of Xilinx, so the Xilinx Vivado has a list of FPGAs. It has filtered all those things, and it has given you three FPGAs with which these specifications are partially matching. So here you can see the second one, that is a part number given as XC. X stands for Xilinx, C stands for commercial, 7 stands for 7 series family of Xilinx FPGAs. In the 7 series, you have 4 different families: Artix, Kintex, Vertex, and Zinc, as per the lowest to highest category. So in the we are dealing with RTX family, that's why it is 7A. 35T means 35,000 logic cells are there, configurable logic blocks in that FPGA. And CPG stands for ceramic package, since that FPGA has a packaged with ceramic package kind of a variant. And 236 refers to 236 number of pins that are available to the FPGA. -1 refers to the speed grade. Actually, I forgot what is the speed grade and all. I will just check and I will let you know what is the significance of speed. So speeds are measured as -1, -2, -3. It is not the speed of or operating clock speed and all. So don't misinterpret. The speed has a different significance. Actually, I forgot this one. I will let you know by end of the day or else by tomorrow. So after selecting the part number, click on next, and it will showing you the complete project summary with all the settings that you have enabled. So once you just go through all the details, and once it is done and you are satisfied, you can click on finish. Otherwise, you can still go back and edit your few options, and then you can click the finish. Once you click on finish, it will try to create a project and it will make enable the environment for you in order to proceed with our lab experiment. I hope I am clear up to till this step, and everyone who are successfully have completed up to this step. Kindly acknowledge, please.
Yes, sir.
Okay, okay. Thank you very much. So now this is the environment that has been created. So this has a lot of windows, and each window has its own significance. So let us quickly understand what are the different types of sub windows available in this environment, and what are the significance behind these windows. On the first window that you see is the flow navigator on towards your left hand side. So the flow navigator, as the name suggests, it is projecting you the all important flows. That is the top-down flow that you need to do in order to complete your entire FPGA-based design. So in the flow, you can see first one starts with a project manager, where it has few settings and the sources. So now you have created a project. Now the project is empty. Now in this project you have to create your design sources. So for that everything, so first entry point is design sources. So for that there are few options and settings that we will see how to develop our sources, how to add our existing sources, and how to use the built-in sources. The built-in sources, we call it as IP, intellectual property core. That means someone has designed the source and they have given a manual for us. So we, instead of writing again the new RTL description for that functionality, we can reuse the existing designs. So those reusability of designs which are already existing one, so those we call it as IPs. So we will see what is an IP and those things. Next, we have an IP integrator. IP integrator, again, as I said, you can use existing IPs, as well as you can create your own IPs from your designs. So if you, now the current trend is IP based designs is the current hot topic in the industry. So wherever you go, everyone will be designing an IP block for a hardware architecture which they are going to prepare. So under this, you can do IP based design, where you can create your own IPs and you can integrate those IPs with the existing IPs, and then you can perform you can carry out your digital VLSS system design through IP integration. So the second entry is called a IP integrator. So that is used for designing with IPs. So first one is project manager. I think that is very much clear. Second is the IP integrator. Third one is the simulation block. So once you have added all your sources, the sources may be your Verilog description, or else your IPs or an existing IP. Once you have designed something, you need to check the functionality. if the functionality is not matching, it is or not desired functionality is not met, then it is you should not proceed with the further steps in the design flow. Why? Because you won't, it will end up in getting a junk circuit but not a desired circuit. So in order to do a rigorous testing and verification of the functionality, it is always advised to do simulation. So for that we have a simulation block. After the simulation, you have RTL analysis thing where you can analyze the RTL level related net list. So once you have the RTL netlist, that you can do, you can transform into the gate level netlist by performing synthesis. So for that there is a synthesis option. Once synthesis is over, you will get a synthesizer netlist. So that is technology independent, as I mentioned you earlier. So that one you need to run the implementation process in order to convert that synthesizer netlist, that is the gate level netlist, into the FPGA based netlist. So FPGA, as I mentioned, it consists of basic logic blocks, that is configurable logic blocks. Inside the configurable logic blocks, you have slices, lookup tables, flip-flops, mux, carry, look ahead logic, and other components of FPGA includes block RAMs, DSP slices, so on and so forth. So the gate level netlist, in order to transform into FPGA netlist, you will do implementation. So after implementation, what you have to do is you have to generate a bit stream. Why? Because you want to deploy it on an FPGA, so you need to program that FPGA with a sequence. That sequence we call it as a bitstream file. So you have to generate a bitstream file. In the bitstream file, you will be having the all the necessary data related to your hardware, as well as where this data needs to be, I mean, where the circuit, in which location of the FPGA the circuit needs to be realized inside an FPGA. So all that necessary information is encoded in the binary format consisting of zeros and ones. This file has a specific format. Actually, we cannot open and read that file. There are, I think, specialized tools are available, but even if you open and read also, we cannot understand anything. So that is a tool generated as per the industry standard. This bitstream file has a zeros and ones, so that's why it is called a bit file. And this file needs to be dumped onto the FPGA. So depending on this file, the FPGA will be configured and the hardware circuit will be realized by using the onboard FPGA resources. So we will call it technically as FPGA fabric. On that fabric, this circuit is being realized. So in order to do the programming and all, for to generate a bit stream, and after bit stream is generation, we have an hardware manager where it will try to detect the board that is connected to your host computer, and once a target has been identified, it will do programming, and then a circuit will be realized. If in case if you have any if you have established a two-way communication by using some specialized IPs, then you can communicate. You can send the data from host computer to FPGA. Again, from you can collect the data from the FPGA to the host computer, and you can visualize it. So all these things will be done under the head program and debug. So this completes the entire design flow right from scratch to the implementation level on the FPGA. So what are the steps that I have covered? In the similar manner, the flow navigator is also just showing you on the left hand side, and it's interpreting that you need to follow the top down approach in order to complete your design cycle. So this is about the flow navigator. After the flow navigator, the major window that you will be seeing is the project manager. In the project manager, we have a name called lab underscore one. That is, in the project manager is pointing to the project that we have created, and the project name is lab underscore one. So under this project manager, we have a few number of sub windows. So the first sub window or the first main window, what I tell is the project summary. As you can see in the middle right hand side, So basically in the project summary, it will show you the overall summary and the current status of your project. So in the overview thing, inside the project summary, you have overview and dashboard. By default, overview is selected, and again you have few settings that you are free to change. And 1 minute. Yeah, you can see here project part number. You can click on the part number and you can change the part number if you want. Like that, you can also change the target language. I don't know why target language is set to VHDL, but I want to use Verilog, so I click on the VHDL. Now the settings box came. Now I will select the Verilog and I'll click on apply and I'll click on OK. So in this way, you can still, even though you have created the environment, you are still free to change the settings under the settings tab. So I request the participants to make sure whether the target language is set to Verilog or not. Otherwise, if it is set to VHDL and if you are writing program in Verilog, it will create an error. So please check. And simulator is mixed, so that is not a problem. Again, you can see here, we have beneath the settings sub window, we have synthesis, and towards the synthesis, towards the right of the synthesis, we have implementation. And the status of synthesis and implementation is currently not started, and there are no errors or no warnings. So if you have performed all these activities, then it will give you the uh, overall summary of these things. At this beneath the synthesis, you have utilization. So after synthesis, it will estimate how many resources that your design architecture will utilize when it is ported on FPGA. So that summary it will give. That is only an estimate. So it will vary. Maybe it may increase or it may decrease after implementation. So whatever the utilization that you're getting after implementation, that is the final utilization or the exact utilization. Again, when you're dealing with the circuits, mostly you will be encountering about the timing and the power. So the timing related information summary and power related information summary will be available in the project summary at the right hand side. So if a timing is not met, then you will not be able to generate the bitstream file. Why? Because your clock is running fast and the data is operating at a low speed. Then there will be definitely a mismatch, and the circuit will be providing will be functioning inappropriately. In by considering this fact, the Vivado tool will not proceed with bitstream generation. So you always need to ensure that you are able to meet the timing with respect to the given clock constraint. Clock constraint in the sense you want your architecture to run at maybe 100 megahertz clock or 50 megahertz clock or a 200 megahertz clock. Then you will be defining that, you will be telling to the Vivado that I want to run my clock at 200 megahertz. Then the Vivado tool, after performing synthesis and implementation, it will find out the what is the critical path, the delay, the maximum delay that you are maximum delay encountered in your circuit. And if that delay is within the clock period, then there won't be any issue. Or if it is exceeding beyond the clock period, then the timing is not met. So in that case, how to achieve the timing at the cost of operating at the same clock frequency? There are some specialized optimization methods, maybe like pipelining or so on and so forth. You need to rework on your architecture in order to reduce that uh, critical path. Or else, if you're free to uh, change or alter the clock frequency, then without doing any further optimization, you can reduce your clock if you're not meeting the timing. Similarly, power estimate will give you the overall power consumption. It will also give a report by specifying what is the static power, what is the dynamic power, and what is the power due to input signals, what is the power due to clock, what is the power due to IO pads. So entire full-fledged report you will be getting from this summary. So beside the summary window, we have the sources window. This sources window is very, very important. Under the sources window, there are four different folders, if you can notice. One is the design sources, second one is the constraints folder, third one is the simulation sources, fourth one is the utility sources. So in this one, design sources, constraints folder and simulation sources folder is very important. Vivado generally maintains a very good hierarchy. So whatever the RTL, HTL descriptions that you will be going to write for developing your hardware architectures, those we all call it as technically as design sources. So all those files will be maintained under the folder design sources. And in addition to that, I told like you need to verify the functionality. In order to verify the functionality, you will be writing some additional code to verify functionality. That code we call it as mm, test bench. So from remember that from the test bench code you won't get any circuit. It is only meant to test the module itself. So those all test benches which you are writing specifically to verify the functionality of your hardware design, those all files comes under the simulation sources. These test benches are used to verify a module functionality. So the simulation sources should also have the design source copy, a copy of the design source folder. Then only it will be able to test it. So in the design sources, you will have only purely design files. In simulation sources, you will have design files along with the simulation files. So that we will see with an example. So I'm just giving only important information. That's it. So at the bottom you have a properties sub window. Maybe if you're selecting any of the file, you can see those properties. So nothing else. At the bottom most you have a wide bar window where you have sub windows. One is a tickle console, second one is message. Tickle console is nothing but it's a tickle language. In industries, no one will use the GUI to open to tool to actually we have here GUI, right, the graphic user interface. So whenever you want to add design source, you'll click on design source. So you are operating in GUI by click and drag and drop kind of mechanism. But industry standards, they will always write a tickle script. It's a piece of a command in order to perform all the tasks. Whatever the task you are performing in this Vivado environment using a mouse and clicking the mouse button, those all things have a dedicated script that we call it as a tickle script. So in industry point of view, people will run the script by a code. So for that you have a tickle console, you have messages, you have logs. So if any errors or warnings are coming in your design, it will be listed under the messages section. And log means whatever the process, whenever you are doing any simulation or a synthesis or an implementation, what the tool is doing at the back end. So how your RTL description is being converted into gate level netlist, how your gate level netlist is converted into FPGA netlist, and how the resources are being utilized, how the tool is doing the floor planning, how it is doing placement, how it is doing routing. Those all things, when you're performing it, a trace back or else a verbose messages will be printed in the log. So it is always advisable whenever you are running any mechanism in the Vivado, immediately switch to the log window and select the appropriate window and try to study the log and understand. So if any errors or warnings are occurring in the log, it will tell you where the problem is. So you have to go there and you have to address that problem. And you have a report section. This is very important. Once a particular task, maybe synthesis or implementation, is being completed, a report will be generated. In the you are advised to go through the report. In the report you will be finding the area estimates, so how the RTL has been converted into a circuit. Once after conversion, what the circuit components, how the circuit has been realized, what are the components which are present in the circuit, like how many gates are used, how many adders are used, how many flip-flops are used, how many registers are used, how many lookup tables are used. Like that it will give you the estimate. So all these things are available in the reports. And design runs is nothing but again it's a kind of a overall summary consisting of power, area and timing estimates. So that's it. I think this brief description will be sufficient in order to understand the layout of Vivado design suite. Okay. So up till here, if anyone is having any doubts, that you can please ask. Otherwise, I will proceed further. I hope everyone is clear with the flow that I have discussed till now. So can I proceed?
Yes, please.
Okay, sir. Yeah. So we will start with a basic combinational logic design. So first what you have to do is click on Add Sources under the Project Manager. You should get this dialog box. Under the Add Sources, it is asking what type of a source you want to create, whether it's a constraint source or a design source or a simulation source. First, we will be starting with the design source. So select the design source and click on Next. Now here it is asking you to add the existing files or else create a new file. So for that, since we don't have any sources, so first we'll start with create file. So you can see create file, so click on create. Now it is asking you on what type of source file I need to create. So select the file type to be very long and give a file name. Uh, Basically now we start with a simple end gate. So I give a end and make sure don't give any names that match with the primitives of Verilog as well as Vivado. Now what you say like a primitive means maybe it's like a reserved keywords in Verilog language or else in the Vivado there are few standard libraries or else some commands with respect to tickle console, so on and so forth. So don't give names which matches with the reserved keywords. And how do you know whether a name is already available in reserved or not? So again, that is very difficult to trace back. So always use any generic name with a special symbol like underscore or any alphanumeric kind of thing. So 99.99% if you use in that convention, it will never match with any primitive. So I gave my file name to be endgate. A and the end I kept it as small. G I kept as capital. A to E I kept as small. So there was no primitive in this fashion. So click on OK. So here you can see one file has been created. It is not in the project, it is not mandatory that you only have a one file. You can have any number of files, and there will be a top wrapper which is collectively holding all the files, uh, collectively holding all the files, that we call it as a top wrapper. But we don't have that much complicated design. We will see what are wrappers in our upcoming lab experiments, but as of now we have only one design file. In case if you have any existing design file, you can click on add file and it will give you a browser window like this. You can just source it and you can add it. So once a file has been created, you click on finish. Once you click on finish, Vivado will do what it will do is it will create a file and it will in the designated location. But before creating the file, it is asking you to specify the port list. So what is a port list? So just So you are creating a hardware architecture for an AND gate. So maybe this is an AND gate. So this is a black box. So if any hardware module, if you take, it has a set of inputs and a set of outputs. So this is called as input port, and this is called output port, and this one is called a module as per Verilog convention. So our module name what we have given is a and the end capital G small a t. This is our module name. We are referring to our module with respect to a unique name, that is AND gate, and this has two ports. One is an input port and the other one is an output port. These two ports combinedly we will call it as port list as per Verilog convention. In the port list we have to define all the ports and type of port, whether it is an input port or an output port. So here Vivado is asking, give the port names, give the direction, whether it is input or output. There is a third category that is called in out, that we will see later on. And if it is a single whether it is a single input or a single output, or else whether it's an input bus or an output bus. So bus means a group of bits, single bit means only one bit. So if it is a bus, you can click on bus. And what is the width of the bus? That means if it is a 4-bit bus, then what you have to do is, if it is a 4-bit bus, you will have bus line 3210. So this is MSB, this is LSB. So how to declare this bus? We will call it as tree down to 0. Tree down to 0. This down to we represent with a colon. So tree down to 0, that means it is 4-bit. So it is not mandatory to define the port list immediately after creating a file. If you want to skip it, you can click on OK, no problem. It will still create a file. If you are sure about the port list, you can give the port list names in that dialog box itself. Then what it will do is it will create a port list and it will generate the Verilog file. If you don't give anything, it will generate a blank file. That is the only difference. So if you see here, we have a keyword called module in the Verilog. This is as per Verilog convention. Module. So module, the word keyword module, when it comes, it identifies that this is a module. So this is a module, it is referring to a module, and the module name is AND gate. Okay, and then there is an opening parenthesis, and finally at the end there is a closing parenthesis followed by a semicolon. So this is very important. This is as per the syntax of the Verilog, and at the end there is an end module. So from the module to end module, whatever you are writing, that we call it as module description. So module description is nothing but a RTL description for which you are going to realize a circuit. So from RTL you have to generate the gate level. From the gate level you have to generate FPGA netlist. From FPGA netlist you have to do bitstream generation. That bitstream you have to load it on FPGA to realize your actual hardware on FPGA. So here what you are doing is you are describing the hardware in terms of high level language, that is Verilog. So from this Verilog language the circuit will be realized. So this is the key principle. So between the module and the end module you have to describe the circuit functionality using Verilog language. So the first thing is after module you have opening brace and closing brace. Within this you have to declare the port list that I told you, right? So for an AND gate, so for our convenience we just consider uh, 2 input AND gate and 1 output. So input is 1 bit, output is also 1 bit. So we consider this as our scenario. So what I do is input A, input B, so I took two inputs A and B and one output C. Here I didn't give any bit length. Even if you want to give bit length, you can give 0 down to 0. That means it is still a 1 bit. If you want 2 bit means you have to give 1 down to 0. Then 2 bit lines will come, 0 to bit line, 1 bit line, MSB, LSB. Single bit you can give 0 down to 0 or simply you can give A. So this is as per the coding convention, or you can simply give input A comma B in a single line and output C. That is also allowed. So I prefer to give each and everything separately. I don't want to club because this is one of the coding style. So generally if you club also there is no problem, but better don't club, write each and everything as a separate entity. So input A is different, B is different, C is different. So let me open my. So my black box is now ready. This I named it as end gate, and the extension of this file is .v, that is Verilog. If you are doing with VHDL, it will be .vhd. So we are not dealing with VHDL, so Verilog, so that is V. And I have given like it has one input A 1 bit and an input B 1 bit and an output C, that is 1 bit. So my black box and inputs and outputs are defined. Now when input and output is coming, it has to do some operation, and that or the result of that operation should come on this line, that is C. So what is that operation? And that I have to define. And one more thing, this one I told it as module, right? So this is module, and this is output port, and this is input port. And what are this A and B? A and B are nothing but these are wires. So wire is a data type in Verilog. There are many data types. In that, wire is the default data type. So A and B are wires, that is input wires. C is the output wire. So here you see I declared only input A. I didn't tell the type of A as a wire. By default in Verilog, A is anything is a wire. So if you want to define also, I think you can define input wire A, input wire B, input wire C. This is also correct. But actually by default anyhow it is wire. That's why we will not declare it as a wire. Anything other than the wire we have to write compulsory. So other than wire, what are the other things are available, that we will see as a later stage. So as of now you please remember these things. So now I have a module, input port, input wires, output wire. Now what is the functionality? If input is coming, what it has to do and what it has to output. So I think everyone knows what is an AND gate. So we have A, B as inputs and we have C as an output. So two inputs means four combinations, 0 0 0 1 1 0 1 1. AND gate gives 1 when both inputs are 1, and in rest of the cases it is 0. So this is the AND gate. So these are inputs, this is output. Now what we have to do is we have to design this circuit, right? So I told you you have to write a description. You have to write description in using HDL language. In our case, it is Verilog. Then this description will be converted into RTL. Sorry, this description itself is in RTL net. This RTL netlist is converted into gate level netlist. If you see in the gate level, your actual circuit should be like an AND gate with two inputs and one output. This is the gate level representation of your module. The module is AND gate. This is the gate level representation. Just a minute, I'm getting an important call. So I'm back again once again. So from the RTL netlist, we get the gate level netlist, right? So once you transform the description into gate level, Vivado should give the gate level netlist in this manner: AND gate with two inputs, each input is a 1 bit, and one output. That output is also 1 bit. So this is gate level representation. But the tool will generate this gate level when you perfectly describe your HDL, when you perfectly write your HDL description in a proper manner by following a standard procedure or a standard syntax given by the Verilog, then only the tool will be able to convert the HDL description into gate level. That is RTL description into gate level. So, what are the standard ways of writing the description? So, there are three different ways of writing the description that we call it as levels of abstraction. A, B, S, T, R, A, C, T, I, O, N. Levels of abstraction. So, you have to write your HDL description with respect to the levels of abstraction. So what any one of the level of abstraction, so or one or more than one, that we will see later. So what are these levels of abstractions that is supported by the Verilog? So first one is the structural level of abstraction. Structural. Second one is data flow. Third one is behavioral. So any description of the any hardware description that you are writing by using Verilog HDL should follow any one or more than one of these levels of abstraction. So you can write the description in structural level of abstraction, or a data flow level of abstraction, or a behavioral level of abstraction, or a mixture of one or more number of levels of abstraction for your module, this module. So now we will see how to write the description in Verilog HDL for an AND gate in these three levels of abstraction, that is structural, data flow, and behavioral. We just take some 5 minutes of break over here, and we will get back and we will see how we have to write all these things. Participants can take some tea break.
Yeah, we will join after 10 minutes.
Okay, sir. Yes.
70? Yes.
Shall we start, sir? Yeah, okay, welcome back. I hope everyone are ready. So we will begin. So I have left at levels of abstraction. So we have structural, data flow, and behavioral levels of abstraction. So in these three different types of abstractions, we will look into it with respect to the end gate. So we will design our end gate using all these three levels of abstraction. So first we go with the structural level of abstraction. As the word structural abstraction refers like a structure. So the structure can be a predefined structure that is existing in the library, or else a user defined structure of any other module. So in this case, what I'm doing is uh, let me take a new page. This is my end module. This is end gate. What I'm doing is in the structural level of abstraction, there is already a predefined structure of end gate available in Vivado or else in Verilog. So that structure is the end gate module. So this is the end gate, and the name is like end. That is the name of the existing structure. Uh, Let me use other color. Okay, no problem. So this shaded one is the existing structure. The outer box is my user defined structure. So it also has two inputs, one out. So what I have to do is this I have to connect to this input, this I have to connect to this input, and this output has to connect to this output. So on top of a black box, my input is A, B, and C, and inside this black displacement we call it technically as instantiation. INSTANTIATION, instantiation. So what I'm doing is an instance of a AND gate structure. I'm taking it from the library and I'm placing it within my module, and I'm making the interconnections. This is called structural level of abstraction. So what I do is I just write AND. It like that you can keep any number of instances. You can instantiate any number of any type of existing or user defined architecture or modules within a main module. So this is like main module. In that you are instantiating sub module. Just like in a C program, you have a main function, and inside that you are calling a user defined function, and outside the main you are writing your user defined functions definition. So like that, you can within the main module you can instantiate any number of submodules. But whenever you are instantiating any submodule, you have to give a unique name for that particular instance. So the instance I am referring is end. This is by default, it is available in library end, and the instance may be any generic name. I give it as G1, and I will close the brackets and I will keep semicolon. So this is one particular instance. Okay. Now how to make the interconnections? In from the user define, I mean from the inbuilt instances, the syntax is as follows: output followed by inputs. So a typical AND gate will have one output and it can have n number of inputs. So what you have to do is to the output you have to connect our wire C, and to the inputs you can connect in any fashion, AB or BA, but more or less it's the same. So what I do is C comma A comma B. So that's it. This is a structural level of abstraction, or simply we call it as structural level of modeling. So our AND gate has been we have described in Verilog HDL successfully. There are no errors or warnings with respect to syntax. How I came to know is on the top right corner you can see a green color square box. So zero warnings, zero errors. If any syntax error is there, say for example here I kept extra comma after C, then that turns out to be red, and it also gives highlighting where the error is. So I can go there and rectify my error. So just save the module. So module is saved. I hope it is clearly visible. The font size is less, but I'm unable to increase the font size. So I will try to check by today. As of now, bear with me. So end gate has been designed. So what is the next step? So next step is to check the functionality, whether it is meeting as per the desired meeting the desired functionality, working as per the desired functionality or not. So that is the immediate step. What you have to do after designing any hardware module, you have to do a testing. Earlier I mentioned you, like for a module, if you want to test it, you also needs to write a test bench in Verilog in order to test that module so functionality. But since this is a simple module, I think for this test bench, if you want you can write it. That is not an issue. Even without a test bench also we can do the simulation. That I will show it today, and tomorrow we will see how to write a customized test benches. So today I don't want to complicate the things on the very first day itself. Why? Because some of the students are still installing the tools. I came to know from Dr. M. Mahesh. So that's why today I will keep it as much simple as possible. But from tomorrow we will increase the pace. So now I will click on the run simulation. Uh, Under the simulation, you can see it is showing run behavioral simulation, and it also has many entities, but currently it is disabled. If you read that, you can see run post synthesis functional simulation, run post implementation functional simulation, like that. Post synthesis timing simulation, post implementation timing simulation. Actually, the simulation needs to be done at each and every stage. initially whatever you are simulating, it is simulating the RTL code and then giving you the response. But the RTL code may give you the correct response, but it doesn't mean like at the circuit level also you will get the same response. There might be a mismatch. So whenever you are performing or handovering the stage from passing the stage from one stage to another stage, at each and every stage you have to compulsorily do the verification process before going to the next stage. Why? Because if any error is occurring, the error is not like logical error. So logical errors you cannot see in the terminal, it will only highlight about the syntax errors. So if the tool, maybe in the hardware description you might have written syntax properly, but tool is not able to understand what is in your mind, and it is not able to transform the RTL description into a gate level netlist, then it will do some trimming somewhere else. And due to the trimming, some of the circuit components might have not been properly mapped. So when it has not properly mapped, then you won't get a piece of hardware over there. And when you don't get a piece of hardware over there, you won't get a proper functionality at the final output. Though the hardware description you have written, which is error free or syntax error free, but the tool is not able to transform it. So you have to always write in a particular manner, not in point of syntax errors. Maybe you are language wise you may be correct, but tool wise tool is unable to transform that description into circuit, means that code is still having a problem. So you should always write in such a way like the tool will able to map the description into an RTL level, or and from the that means a gate level. So from RTL to gate level, you should be able to get a perfect mapping. So you have to write always in that particular manner. So how you know whether your RTL has been perfectly mapped into gate level and your gate level netlist is perfectly mapped into FPGA netlist? So once the mapping is over, again if you run this time the simulation with the post after synthesis, that we call post synthesis functional simulation, the simulation process now instead of running on the HDL code, it will run on the synthesized netlist, that is RTL netlist, that is like gate level netlist. So the same simulation will be run on gate level netlist, and if you are getting the desired functionality, that indicates that your RTL has been perfectly mapped into the gate level netlist. And again, after implementation, what you are doing, the implement gate level netlist you are transforming into FPGA netlist. So once you get the FPGA netlist, again you have to run the simulation, and that simulation is called post implementation functional simulation. So after in this simulation, what it will do is the simulation will run on the implementation netlist. So the implementation netlist consists of basic building blocks of the FPGA. So again, if you are getting the desired output, then it indicates that your gate level netlist has been perfectly mapped into the implementation netlist. Then it is like error free, and you can expect the desired output even when you put your real circuit on FPGA. In the somewhere down the line, during the synthesis or implementation, when you're running the simulation and you're not getting any the desired functionality, then it is waste to proceed further. Why? Because ultimately you won't get a proper circuit that matches that works with a desired functionality. So simulation is plays a very key role in verifying the functionality of your design. So now we are in, since we are at the basic RTL level, we have to do a very quick simulation with the RTL description. So that description is called as run behavioral simulation. So under the simulation, you click on run simulation, then you will get a menu. In that you click on run behavioral simulation. So it will run the simulation and it will create a simulation environment for you. A new window will open to you. Yeah, now you can see actually mine from it is coming at a white background. Why? Because I have changed the color. I think for you it will come as a black background. Over on that you will be getting the signals with either red, blue or green color, if I'm not wrong. So this is a simulation environment. So on the simulation environment, you can see it has stopped at timestamp of 1000 nanoseconds. You can see on the screen the simulation stopped for, at a timestamp of 1000 nanoseconds. By default, the simulation will run for 1000 nanoseconds and it will stop. Beyond that, if you want to run, you have to provide how much time you want to still run the simulation. But for simple designs, this is more than enough. For very complicated designs, you may require to run the simulation up to a 1 second or a 2 second. So that is very rarely used. So by default, it will run for 1000 nanoseconds and it will stop at the end. So if you want to have a fit view, if you want to see the timestamp from 0 to 1000 nanoseconds, here you can see zoom fit option is available in that terminal. You click on zoom fit, it will give you a concise view with a timestamp starting from 0 nanoseconds to 1000 nanoseconds. Okay, is it clear? Now you can see here A and B are at high impedance Z and C is a unknown value. So since we have not connected in the test bench environment, so actually you need to know what is a test bench again here. Let me open. Now we are talking about a simulation, right? In this simulation, we have our module. Actually, we are simulating with respect to test bench environment. So that we call this TBE. As of now, we have not written any test bench, but generally we will be having a test bench environment. This test bench environment has some set of inputs and has some set of outputs. What we do is test bench inputs we take and we connect it to module inputs, and module outputs we connect to the test bench outputs. So we are the user, we are sitting here, we are observing the outputs from given by the test bench environment, and we give the inputs at this end. We give inputs to the test bench environment. These inputs from the environment will go to the module which is sitting in middle, and a module will generate the outputs. That outputs will capture through the test bench environment outputs and we will observe it. So this is a test bench environment. Currently the A and B are having high impedance. Because we have not given any inputs at the input side. These inputs we call it as stimuli. STIM. More than one input we call it stimuli, otherwise we call it as a stimulus, and then we observe the generated outputs. Okay, since we have not given any stimuli, so inputs are at a high impedance, that is Z, output is unknown, that is X. So what we do is you click on A, select A, click on right click, and here there is one option called force constant, and it is asking what is the radix value. So this is a binary, select binary, and force value, with what value you want to force this input. Say for example I force with 1 and click OK. Similarly B, I'll select B, right click and click on force constant and click on a value again 1 and click OK. Now the values are given. You just run this simulation for a fraction of seconds, maybe 10 nanoseconds. So 10. In the timestamp, I entered 10 and press enter. I think it is very small. Better I will run for 100. Okay. Now you can see I will enlarge it. So here the input is A is 1, B is 1 and output C is 1. So from here you can see we are getting the outputs. Input, we gave it inputs, we immediately got the output. And any one of the input, maybe I will select B, again right click, force constant. I will make this output to 0. Input to 0. Click on OK. And now again I run the simulation for 100 nanoseconds. Now you can see input A is 1, B is 0, and finally output is 0. And this input is kept constant at the same level for all the time. That's why even if you run the simulation for n number of nanoseconds, the instance inputs is not changing, output is also not changing. So I will click on zoom fit. So this is the output.
Hello,
So
sir.
yeah, sir, tell me, sir.
Sir, but our screen is not as same as yours.
What, sir?
Here, whatever we are doing here is not same as what you are displaying. Can I share my screen?
May I know who is this speaking, sir?
Sir, this is Mahesh.
Sir, yeah, tell me, sir, what is the problem?
Actually, the outputs, the variables or the binary constants, what we are varying, that is not being reflected in the waveform.
Not reflected in the waveform.
Yeah, it's
On the
like
left
a
hand side,
blue,
on the left hand
it's
side.
like a it is still in the high impedance state. The graph is in high impedance state.
Okay, but here you can see the value, sir. What are the values? A, B,
Yeah, I'm able to see the values.
are you able to see numerical values or high impedance values?
Binary values, I'm able to see, but the graph is showing Z, Z, and X, high impedance states and unknown.
Have you run the simulation, sir?
I have run, sir.
What is the timestamp?
Timestamp is 100 nanoseconds.
You just run it for another 100 nanoseconds, sir. Even then it is coming like that. Can you just share your screen, sir? I will see. I will stop presenting my screen.
My screen is visible to you, sir.
Yes, sir. Click on zoom fit, sir. Zoom fit. Yeah.
Yeah, I already did that, sir.
Now it is up to 1000 nanoseconds. It is like that. Now you run for additional 100 nanoseconds, sir. Not that play button.
Well,
Don't click on play. Don't
okay.
click on play. There you type 100. 100 and press enter, sir. Now you are able to get, yeah.
Then what is this play button, sir?
Actually, you have to enter the time here and you have to click on the play. So up to those many nanoseconds, it will do the simulation. So by default, it already reached 1000 nanoseconds and you are also given 1000 nanoseconds. So if you keep pressing on play button, it will not run the simulation. So if you want to use that, what you do is uh, what you can do is you have to change the value. Maybe now it is in 1100. Maybe you give 2000, sir. In the time you give 2000. Now you click. Now you click on run. I think it is already run. You got up to 3000.
How to clear this at least? Clear and do that.
You have to click on relaunch, sir. On the right hand side top, after the time, you have a circle button, right? Anti-clockwise direction. Right, yeah. Click on relaunch. Now you click on run, sir. First you give the values. Yeah. Wait. Wait, sir. Values are not updated, I think. Once check, it is still showing Z.
Yeah, it's working, sir.
Okay. Yeah. Okay.
Right. Thank you.
Okay, sir. You can stop presenting so that I can share my screen.
Explain me.
Okay, is it clear now, sir? So in this way we can verify the functionality. So next what I do is we have seen the structural level of abstraction, right? Now we will proceed with the data flow. So this is completed. Now we are going for data flow. So in data flow, as the name suggests, you are purely defining the how the data flows from the input to output. So you want the data um, data A and data B should be made logical end, and the resultant value should flow to the output, that is C. So what you have to do is C is equals to A ampersand B. This is somewhat like data flow, but it's not purely data flow. You have to give the keyword called assign, ASSIGN. Assign C is equals to A ampersand B. So why you should not use C is equals to A and B means, if you use like this, C is equals to A and B, this is a procedural statement. So we have to note there's a one more concept in Verilog. Dr. Mahesh sir, can you please mute your mic? I'm getting disturbance. Uh, so in Verilog language, there are two type of statements. One is non-procedural statements, and second one is the procedural statements. So here, if you write C is equals to A ampersand B, this comes under the class of procedural statements. So I will tell you what is a procedural and non-procedural. In data flow, we mainly use non-procedural statements. So how we will identify is like this is assign C is equals to A and B. So for time being, you have to write assign C is equals to A and B. And one more very important concept in Verilog is Verilog is not sequential. It is not a sequential programming language. It is a parallel language. Means unlike the C language, what you do is you have line 1, line 2, line 3, line 4, so on. The flow of execution is sequential. So one line, this line is executed, after that it goes to next line, after that it goes to next, after that it goes to next. But Verilog is parallel. So you have a piece of code, these two may run at same time, and these two also may run at same time. So this is not a sequential programming, this is parallel programming. Why? Because in hardware we don't have the concept of sequential. In hardware maybe you have a block, a chain of modules. These all modules may run independently. So if they are running independently at time t is equals to 0, this should also work, this should also work, this also should work, this also should work. If there is any data dependency, this will wait for the data to arrive from the previous block. But that is only for data only, it is waiting, and that waiting is done with respect to the sensing of control and status signals. But the module is still under working. At time t is equals to 0, all modules are working, and the way each module performs operations depends upon the control and status signals that you are giving, that you give, and the data signals that you drive. So that only varies, but at the time t is equals to 0 and t is equals to infinity, until you switch off your hardware, all modules are working in parallel. So that's why in Verilog language also supports the scheme called parallel execution. Actually, we should not use the word called execution. Here we are not executing anything. We are writing a Verilog description language to realize a hardware that runs in parallel from t is equals to 0 to t is equals to infinity. So, uh, but you, for all the hardware description, you are writing in Verilog language. Now you should know very much clearly which set of statements run in parallel, which set of statements run in sequential, means one after the other. As I told, Verilog supports parallel. It doesn't mean everything it will run in parallel. It also some part of the functionality it also runs in sequential. In C, it is completely sequential, but Verilog sequential with parallel. So, in order to avoid this confusion, so what Verilog language uses is the concept of procedural and non-procedural statements. So, in the Verilog code itself, so you have a long piece of Verilog code. Okay, this is a long piece of Verilog code. In this long piece of Verilog code, you have to define a block of statements. This is one block, this is one block, maybe this is another one block. These are called as blocks. So blocks of statements. These blocks are called as procedural blocks. And what are the statements that you write in the procedural blocks are called as procedural statements. Okay. And if you look into this, all the statements inside a procedural block will run in sequential manner. Next, all the procedural blocks will run in parallel manner. And here one thing you have to take into consideration. A statement means uh, you have left hand side equals some right hand side. This is a statement, right? Say for example, A is equals to B, or in our case, C is equals to A and B. This is our example, right? So any statement has left hand side and right hand side entity. So this is called, from right hand side, it is getting assigned to the left hand side. So whatever the things that you are using on the left hand side, these should be local to a procedural block. Okay, why? Because suppose we have a C is equals to A and B in first procedural block, and in second procedural block you have C is equals to D or E. Now if you see, C has multiple drivers. In one procedural block, C is driven with A and B. In second procedural block, C is driven with D or E. So this is illegal in terms of Verilog. Why? Because you cannot have multiple drivers for a common net. This C is called net. Even AB are also called as net. Net means just kind of a variable. In C, you will call it as a variable, but in Verilog, we will call it as a net. Net has many types. First type we have seen wire. The net type is wire. Okay. Earlier in the inputs, we have defined like all inputs and outputs by default, they are wire, right? So in that manner. So you cannot have multiple drivers for a common net across two procedural blocks. Why? Because two procedural blocks I told like they are running in parallel. So at the same time t is equals to 0, you cannot drive the C net with two different values, that is A and B and D or C, D or E. So that is illegal. So whatever the nets that you are using on the left hand side of a procedural statement, they should be local to a procedural block. So this is an important concept, like procedural statements. And one more thing, if C is equals to A ampersand B, if you write like this is a procedural statement, right? This you have to write inside a procedural block. Inside a procedural block, all the left hand side, whatever you are having, the nets, they should be of reg data type. The right side nets, that is in this example A comma P, they can be anything. It can be a wire or it can be a reg, but assignment always to the left hand side should be a reg data type. Reg in the sense like it is, don't misinterpret as like it is a register, because the tool sometimes it may realize it in the form of a register if you provide a clock signal. If you don't provide a clock signal, it is a treated as a reg type, but it is not actually a register. Reg has no hardware significance. Reg and register are different. Reg is a data type. That's it. So in the data flow, what you have to use is, we have to use, I told like assign C is equals to A and B. This is a non-procedural block. In the non-procedural block, the left hand side net, this is by default a wire. The right hand side, it must be a wire. Left hand side must be a wire, then only you can assign. Right hand side can be a wire or a reg. So this is a big difference between procedural and non-procedural statements. So in the data flow, what we have to write is assign C is equals to A and B. So this is data flow modeling. So now what we do is, again we just run the simulation one more time and we just check whether it is okay or not. So quickly again I give data and I run the simulation. So for 1 0 the output is 0. So it is working. So we have seen the data flow modeling as well. Next one is the behavioral modeling that we will cover now. As the name suggests, behavior. We are just interpreting the behavior. we are describing the behavior of our AND gate, and we are asking the Verilog module to synthesize into a gate level netlist. So how a AND gate behaves? We have seen a truth table of a two input AND gate, A, B, 1 bit input and C 1 bit output. So this is a truth table. So this truth table itself is telling the behavior of our circuit. So how our circuit behaves. So when you get a 0 0, the circuit behaves and gives an output 0. Like that, when 1 1 comes, the circuit accordingly generates 1. So this is the behavior of our circuit. Merely describing the behavior of a particular module gives you the behavioral description. Again, this behavioral description, data flow modeling, wait, just a minute. So data flow modeling, we will use non-procedural statements, as we have seen, like assign. For behavioral modeling, we will use procedural statements. Now we will see how to define the behavior. So non-procedural statements always start with a keyword called assign. But how procedural statements will start? Procedural statements will always start with a keyword always, some begin and end. And here you have to define always at the rate, and you have to do parenthesis. Inside the parenthesis, whatever you will write, that is called sensitivity list. Means I will take a new page. So we are writing a procedural block. So this is always. So this block will be sensitive. Means this block inside always will be having statements, right? Procedural statements. And these statements run in a sequential manner. And when these statements should really affect, means when the circuit should work, it should work continuously all the time, that you have to define always at the rate star. Always at the rate star. As long as the power is there, it should work continuously. That is the meaning. This notation is used for combinational circuits, whereas in sequential circuits we have to operate with respect to clock, right? So in that case, what we write as always at the rate, whether it is a positive edge of the clock, then you will write percentage of clock. If it is a negative edge, neg edg edge, clock is a net. So always at the rate neg edge of the clock. It's not necessary like you give only one list, sensitivity list. You can also give any number of n number of nets. So whenever there is a change in a one particular net is been observed, then the entire statements are executed. Actually, I should not use the word executed, but for your understanding I'm telling. So whenever a change in the change in the value of the variables or the nets that you declare in the sensitivity list, so the syntax goes like this: always at the rate bracket, and whatever the nets you write in this bracket, this is called as sensitivity list. So whenever any nets which are mentioned in the sensitivity list changes, then the always block is executes, and it runs in a sequential manner, one after the other, and generates the corresponding outputs. So that is the case. And how to write these statements? What are the procedural statements? How do you write? I told earlier C is equals to A and B. This is a procedural statement. Left hand side should be a reg type. Right hand side can be a reg or a wire. So this is okay, fine. Apart from this, whether there are any special procedural statements in Verilog? Yes, there are some special special procedural statements. The most common thing is if, begin, end, else, begin, end. Here you can write statements. Here you can write statements. This is one case. Other procedural statement is case, end case. Here you give some value, begin, end, again some value, colon, begin, end. So these are the syntaxes. So here what we do is we define a procedural block always at the rate start, begin and end. Inside we write a case. Inside the case followed by end case. Inside the case I will keep two flower brackets. In those two flower brackets I will write a comma b. Why? Because we have two two nets we need to scan with respect uh, to define the output of our AND gate. So since we are taking scanning two lines A and B, in this case list we kept A and B. If A and B combinedly, if it is 2 tick, this is the notation. What it has to do, C is equals to 1 tick B0. This is a notation. Like that, if it is 0 1, 0 1 means 2 bits, right? So that's why 2 tick binary 0 1. Then what it has to do, 1 tick, likewise 1 tick, similarly 2 tick 1 1. That means A is equals to 1, B is equals to 1. So that's it, completed. However, it is showing error. Why? Because here we are assigning C is equals to 0 0 0 1 in each and every case, but I C is on the left hand side, right hand side value is getting assigned to the left hand side net, and the type of net here C, from this notation it is a wire. Why? Because it is an output, and output default net type is wire. But inside the procedural statement, left hand side should be of reg type. So what you do is, after the output C, you declare a type of the net instead of wire to reg. Now that error will go and you get strong in defining the type of the output as a reg. There won't be any functional changes at all. But however, you will get the output. This is as per the convention of the Verilog. Or else you can do one thing. You can still keep it as a, and what you have to do is you have to edge some, maybe some capital C, for example. What you can do is capital C is equals to 1 take B. Then you can write one assign statement. C means from the reg type you are driving the wire type. So this is also one of the valid notation. if you want to still preserve the type of net output type to be wire, then you can do it in this way. However, this is not necessary. I'm getting an important. Yeah, sorry, this will be reg type. Reg C. This is done. This is the behavioral modeling. If you just want, you can just do a quick simulation. I just change the value for outpost. And from the simulation. So we got the expected output. So in this way, uh, we can design the hardware circuit either in structural, behavioral, or data flow, or a mix of either one, two, or all the three, depending on the complexity of the design. There is no thumb rule for designing any circuit by any of the fixed level of abstraction. So it always depends upon the end user. So in some cases we can design in all the levels of abstraction, but in some complex designs we don't have, we won't always draw a truth table and find the values, because if the variables are increasing, it is very difficult to find the truth table. So for all those cases, we will directly adopt the behavioral level of modeling or data level of modeling. Maximum we will avoid the structural level. Structural level we will do only we are clear about the structure, what are the gates which it is going to handle. Otherwise, by behavioral or data flow modeling, we will do it, and we will leave the control to the tool. So the tool will do the mapping and it will generate the equivalent gate level netlist. So that's it from my side for today. I hope I have covered all basic topics. From tomorrow, we will see with the combinational logic implementation in Verilog. And then we will proceed with some advanced designs of designing finite state machines. After that, we will increase the level of complexity, and we will have some more hands-on session. So I think Dr. M. Mahesh sir will be giving you some small kind of homework exercises on my behalf. You can go through all those things and try to practice. Try to design any logic gates, and then any combinational circuits like half adder, full adder, multiplexers, decoders, encoders, like that, by using any of these abstractions. So we will meet tomorrow and we will continue this session. That's it from my side. Mahesh sir, please take the control.
Session. We'll meet you tomorrow again. Bye, sir. Thank you very much. We'll meet you again.
Uh, Dr. Mahesh sir, can I close from my end?
Yes, sir. We are into the closing, and sir is just addressing the students about the software and the homeworks. We'll be meeting tomorrow, sir.
Okay, okay, sir. Thank you for the update.
Okay.
Okay,
Thank you,
sir.
sir, for
Thank
this session today, and it was very good, sir.
you. Okay, okay, sir.
Thank you, sir.